So my name is Vijay. I'm a machine learning specialist. I work for Google. Hope you're all having a good day today so far. How many people saw the last talk in this room, the Meaning of Life talk? Okay, good. And that's actually a good natural segue into this talk, because that talk was kind of the grand vision of artificial intelligence, some of the big milestones. And this talk is going to be very much practical knowledge. If you in the audience want to build a machine learning model, how do you do that? So credit to the conference organizers for planning it like that. How many people have built a machine learning model before? Okay. And how many people have specifically used or at least played around with TensorFlow before? Okay, good. So the flow of this talk is going to be the first 15 minutes or so are going to be slides, and then we're going to spend the bulk of the time actually building a machine learning model end to end. I'll actually show you the code, execute the code. This will be the largest screen that I've ever run live code on, so hopefully it doesn't go too badly. So when I say end-to-end machine learning pipeline, this is what I mean. So you start with a raw data set. You do some pre-processing on that data set. Then you train your model. You deploy that model to some place. In this case, we're going to deploy it to the cloud. And you run some predictions against that model. And specifically, the problem that we're going to work on is predicting housing prices. So we'll actually start with the raw CSV file and then go through the whole set of instructions there. So before we get into that, just a couple slides about machine learning within Google. So most of you probably know that machine learning is pretty central to what we do as a company. We are ultimately a data company. And so this is a chart that shows the growth of machine learning models in production in Google over time. So you can see even at Google, back in 2012, this was very new for us. And fast forward to today, we have over 4,000 machine learning models in production. And it's gotten to the point where now within Google, machine learning has become an expected skill set for every developer to have. So you don't have a special set of data scientists over here and then your web developers over here. Machine learning knowledge is becoming as common as knowing Java or Python within Google, and we offer training courses and programs for every software engineer within Google to get competency within this field. So these are some of the products that we use machine learning in. It's in almost every one of our consumer-facing products, so it's a big part of the ranking in our search algorithm using an algorithm called RankBrain. Google image search relies on machine learning. Gmail spam classification. There's a new feature in Gmail that some of you may have seen called Smart Reply, where it actually tries to predict an appropriate response to your email, so you don't have to type it manually, which is quite useful. So then when we talk about Google Cloud Platform, that represents the externalization of all of this internal work we've done on our own products. So we have very large research teams. Last year alone, we published over 300 research papers in top-tier academic journals about machine learning. And what we've done is we've taken some of these models and made them available to the public. So all of that falls under the Google Cloud Platform umbrella, and you can form a division within that. On the left side, you have your custom machine learning models, and on the right side, you have your pre-trained machine learning models. So most of this talk is going to be about how do you build a custom machine learning model. But I do want to touch just a little bit on the pre-trained machine learning models so you know what they are and how to use them and when you would use them. So these machine learning models, typically, as a general principle, you always want to start with the simplest solution and add complexity as necessary. So there's some problems that you can solve without building a model at all. And if you can do that, then that's what you would want to do, because there's much less engineering effort, and you don't have to reinvent the wheel. And these are all very low barrier to entries. You can actually trial these. You don't even need a Google Cloud account. You just go to your browser, go to the respective page. So this example here is our Vision API. And you can just drag in an image, and it'll show you exactly what it will return. So in this case, it's giving me a bunch of labels about this image with a confidence score for each one of these. So for example, it's 85% confident that this is a suspension bridge. There's some other features here. There's a landmarks feature that actually recognizes certain landmarks, so it knows that this is specifically the Golden Gate Bridge in San Francisco, and it gives me the lat-long coordinates. And when you're calling it over the REST API, you'll get your results in this JSON format, and you can integrate it into your application as you see fit. So the best way to think about using these pre-trained APIs is as Lego blocks. It's very unlikely that a single pre-trained model is going to solve your specific problem entirely by itself, because by the nature of a pre-trained model, they're trained on Google's data. It's trying to be a one-size-fits-all solution, so we train on massive data sets, but it's a very generalized data set. And in your applications, you're working on very specific problems. So here's an example of a customer out of Japan that built a platform to auction off cars. And they wanted to add a functionality where if they uploaded an image of a car, they would have an API that would return certain information about that car. So it would tell you what is the make of the car, what is the model of the car, if it's a specific part of the car, what part of it is. Is it the tires, is it the steering wheel? And also, what side of the car are you looking at? Are you looking at the front or the left or the right of the car? And the reason that this was important is because that's how they categorize these images for their consumers to look at on their website. So before machine learning, they had actual humans go in and tag each of these images, and this is the left side of a Ford Focus, et cetera, very time-consuming. And they wanted to try to use machine learning to automate that. And what they did at first was a common mistake, which is try to build a single model that solves that entire problem, that spits out all of the information that they care about from a single model. And they invested some significant engineering effort and eventually gave up because the model just wasn't giving the results that they needed. Then they took a step back and said, what if we break this into multiple pieces? So they said, first, let's use Google's pre-trained models and see how far that gets us. So they ran their images through our Vision API, which is zero engineering work on their part, because we've already done the model and exposed it. And they've noticed that solved part of the problem. It tells you what is the make of a car, but not what is a specific model. And it also can identify what part of a car it is. Is this a tire or is this a steering wheel? But what it could not do is, for example, tell you is this the left side or the right side of a car, because it just wasn't trained to do that. So now when you narrow the scope of the problem to just that, it's actually quite easy to build a custom model that does that using a framework like TensorFlow. You get 1,000 images of left sides of cars and 1,000 images of right sides of cars, different types of cars, and you put them through a neural network, and you get a pretty robust algorithm that can now tell the difference between the left and right side of a car. And that solves part of the problem. So they did this in a piecemeal approach and then aggregated the information from each of these individual models, these smaller models, to solve the total business problem. And they ended up getting where they wanted to be, but in a much faster and cleaner way. So that's really how you should think about these problems. Is a lot of times you can make them modular, and a series of smaller, simpler models can aggregate to solve what you're trying to solve. Okay, so that's it for pre-trained models. Now, let's say you do need to build a custom machine learning model. You have narrowed the scope of it as much as possible to use things that were already built, so you're not reinventing the wheel, but usually there is at least some part that you have to build custom. And when I say custom, that means you're training on your own data, you're writing your own code. And the framework that we at Google internally use for this type of thing is called TensorFlow. So TensorFlow is something that probably most of you have heard of. It seemed like about a quarter to a third of the room has actually already used. So first of all, what is TensorFlow? TensorFlow is a machine learning framework. It was open sourced by Google in November of 2015. And since it has been open sourced, it's become the most popular machine learning framework. And I'll talk about some reasons to why it may have become so popular. So one is, it's worth mentioning that the popularity of TensorFlow itself is a big reason to use it, because with popularity comes developer ecosystem. So if you're working on a problem, chances are someone has already solved a problem similar to it using TensorFlow, and you could do a search, and you'll find a blog post, if not an official TensorFlow.org tutorial, showing you a code template, and you can use that to bootstrap your own project from. So that's very valuable. And the second thing there is, if you get stuck or you run into a bug, when you post it on to something like Stack Overflow, because there's such a large community around it, you're typically going to get a response faster than if you're using a lesser used framework. So the popularity itself is a big asset at this point. Another reason that TensorFlow is popular is this idea that you can program it at various levels of abstraction. So if you don't need a lot of control over your algorithm, if you're not a researcher that's tweaking your algorithm down to a very fine level of granularity, then you can abstract yourself away from that using a higher level API like Keras, which some of you may have heard of, or like the estimator API, which is actually the code that I'll be showing later on in the talk. And this allows you to do things like just use a quote-unquote canned model that's pre-implemented for you. It already has the training loop built in, already has the evaluation loop built in, and with just a couple lines of code, you call that, and it saves you a lot of work. But if you do need additional flexibility, you can drop down a level in the hierarchy to these lower levels, ultimately down to the base vanilla TensorFlow level, where you're explicitly defining your matrices and doing your matrix multiplications at that point. Another reason TensorFlow is popular is because it's production ready. So the reason Google created TensorFlow in the first place is because historically, the deep learning frameworks that existed at the time all came out of academic institutions. So MXNet came out of Carnegie Mellon, Theano came out of the University of Montreal, Café came out of the University of Berkeley. And if you think of the needs of an academic researcher, it's very different from the needs of someone who's in industry. So a researcher, their motivation is essentially to prototype something so that they can prove out a theory, publish that theory in an academic journal, and then move on to something else. So there's no real thought about how do I scale this model, how many users are going to hit it, what are my security considerations, and things like that. So when Google got into this machine learning space, knowing that everything they built was going to be used by millions of users, they had to create a tool to solve this problem that didn't exist before. So all of these things, like serving and latency, are first-class citizens in TensorFlow, and they're built into the tool. So it's very performant, and you can also deploy it across different types of hardware. So you write your code once, and then you can deploy it on a CPU or GPU or on a mobile phone, Android or iOS, or even on embedded devices like Raspberry Pi. And of course, algorithms. So the main reason that you use a machine learning framework is so that you don't have to re-implement algorithms that are already well-established and well-proven in industry. So this is an example of the TensorFlow Object Detection API. It is an algorithm that identifies labels in an image, and not only does that, but it draws bounding boxes around those labels. So this is a much harder problem than the the original type of computer vision problem, which was image classification. That would tell me that there's a kite in the image somewhere, but it wouldn't tell me where within the image that kite was, or it wouldn't tell me how many kites are in that image. So this is an algorithm that came out of Google Research, and then we open sourced the results of this via TensorFlow. So now you can actually leverage this algorithm with a few lines of code. And if you just do a Google search for TensorFlow Object Detection API, you'll see a blog post that tells you how to do that. And here is another example. This idea of a wide and deep algorithm is no longer really considered state-of-the-art. But when it came out, TensorFlow was the first popular framework to kind of distribute this or democratize this type of modeling to the quote-unquote common man. So the idea of wide and deep models is you have this thing called deep learning, which works very well for dense data sets, and you have linear models, which work very well for sparse data sets. And the idea is quite simple, which is what if we combine the best of both worlds and have the deep model work on the dense features and the wide model work on the sparse features, and then combine the results at the end. And that's called wide and deep learning. And that was another example of an algorithm that TensorFlow really brought to the general public. Speed. So, of course, when you're thinking about deploying something for production, especially if it's going to power a website or you have some real-time need for it, then performance becomes very important. So TensorFlow is very transparent about its benchmarks on different problems, how it scales horizontally. And you can go to tensorflow.org/performance/benchmarks and just see the tests we've run and see exactly what our performance is and how it compares. And then the last thing I'll say about TensorFlow is the reason why you have this trade-off of it both being developer-friendly, written in a language like Python, which is considered developer-friendly but traditionally considered slow, but also very performant, is because the output of your TensorFlow Python code is what we call a data flow graph, which looks like this. And this is actually visualized using a tool called TensorBoard, which I'll also demo. And that graph is just a series of instructions that is then interpreted by a C++ backend. And the C++ backend takes care of how do I compile this code in a very fast way and specific to the type of hardware that I'm instructed to run on, whether that's a CPU or GPU, for example. So that's TensorFlow as a framework, why you would want to use that for your custom machine learning modeling. And then why Google Cloud Machine Learning Engine? So basically, why would you do this in the cloud? So the first thing to state here is a lot of times you don't need to do it in the cloud. As a rule of thumb, if you can train your model in under an hour on your local laptop, just stick on your local laptop. But at some point, if you're using large enough data sets or you're using complex enough algorithms, you're going to hit that bottleneck where the training time on your computer, your compute power essentially becomes your bottleneck to creativity and development, and it'll stop you from trying different ideas, or it'll stop a problem from being tractable altogether. And that's when you want to make the jump to cloud computing, because essentially then you have access to a supercomputer over an internet connection. And the tool I'll actually be using today is called Google Cloud Machine Learning Engine, which is a managed TensorFlow service, and it gives you some nice things. For example, it makes horizontal scaling very easy. You just specify, I want to run this across 10 GPUs, and Google will take care of spinning up the infrastructure for you, provisioning the virtual machines, and then spinning them down when your job is done. It has an automatic hyperparameter tuning function, automatic monitoring, logging, versioning, a built-in auto-scaling prediction service, and coming soon, you'll have access to tensor processing units, which I'll talk about on the next slide. And there's no lock-in. So because TensorFlow is an open source framework, once you train your model, even if you use our product as your supercomputer to give you the horsepower to complete that training in a reasonable amount of time, the result of that is an open source model. So you can download that model, you can deploy it on a phone, you can deploy it on premise, you can deploy it anywhere you want to. And the reverse is true as well. You can train your TensorFlow model on your local laptop, but you can deploy it to our cloud just for the prediction service, because maybe you're expecting hundreds of thousands predictions per second, and you don't want to build out your own infrastructure to handle that. So you can train on-premise and deploy for prediction in the cloud as well. Tensor Processing Unit, for those of you who haven't heard of this, this was the hardware that powered the artificial intelligence that defeated the Go champion. If you heard of that, it also powers Google Translate and a bunch of other internal applications. And we've now made this available to the public in alpha at this point. And just a hardware comparison to give you kind of a scale of how powerful these things are. A tensor processing unit can process 180 trillion floating point operations per second. An NVIDIA K80, Tesla K80 GPU, which is kind of the de facto cloud GPU at this point, is 9 teraflops. So this becomes actually more important for inference than training, because in training you can always just scale horizontally. So you could use 20 NVIDIA K80s and you'd get a similar speed to using a single TPU. You just have to do the price performance calculation. But when it comes to inference, also known as prediction time, and you need to get that result back within milliseconds, the overhead of horizontal computing actually becomes more, will take you out of your real-time requirement. So at that point, vertical scaling on a single chip becomes important, and that's when using these advanced chips like TPUs becomes more important. Okay, so on to the actual problem that we're going to build an end-to-end solution for. So what we're going to do is predict housing sale prices. And so I'm going to start by asking you, the audience, to make a prediction on a simple data set. So my data set is a 1,000 square foot house sells for $100,000, a 3,000 square foot house sells for $300,000, and my question for you, and you can just yell it out, is how much would a 2,000 square foot house sell for? 200,000, but it's pretty easy, right? So let's make it a little bit more complicated. Let's add 2 more features to my data set. So in addition to just square footage of a house, I'm going to predict the housing price based off of what is the crime rate in the area, and also how good are the schools in the area. So now, I'm just going to let you read this slide. And the question is, how much would a 3,000 square foot house with a crime rate of 30 and a school rating of 2 cost? Any brave souls want to answer? Yeah, it's not so easy now. And that's just with 3 features. So imagine if you had 100 features, and imagine if you had millions of rows. This is where you now need to use machine learning to make this type of prediction. So this is the problem that we're going to be working on. So in order to solve this, and actually, by the way, if you want to recreate this lab after this talk, this is the short link to some documentation on how to do that. So you can snap a picture of this. Also, you'll have access to the slides through the conference website. Okay, so to actually do our development, we're going to use a tool called Data Lab. So Data Lab is basically a white-labeled version of Jupyter or IPython notebooks. How many people have used Jupyter or IPython notebooks? Okay, so it's a good way to combine your code with documentation in a way that's kind of digestible and easy to share and collaborate. So within this notebook, I'm starting by just importing the frameworks that I need to use. So in this case, I'm using Pandas, which is a framework that enables me to deal with the CSV data that I'm going to use easily and parse it, and then, of course, TensorFlow. So I'll just execute those 2 cells. And it's always a good idea to know what version of TensorFlow that you're dealing with, so you can debug any version conflict issues. So I'm using TensorFlow 1.2. And we talked a little bit about this idea of TensorFlow APIs and the hierarchy. So in this case, I'm going to be programming at these top 2 levels, the experiment and estimators API. And the main reason I'm going to do this is, one, it makes for less lines of code. But the other reason is it gives me distributed computing for free. So as long as I stick to these higher level APIs, then TensorFlow just understands how to run on 10 GPUs versus 1 GPU, and I don't have to make any code changes, which if you've tried to do distributed computing across multiple CPUs or GPUs manually before, you'll know this is a big time saver. It saves you a lot of headache. And so the actual steps that we're going to go through in this notebook are, one, we're going to load in our raw data. We're going to write our TensorFlow code, and that's going to have some steps broken down, which I'll explain. Then we're going to package that code up so that we can train it in the cloud. We're going to inspect the results of that training using TensorFlow to make sure that we're happy with our accuracy. Once we're happy with our accuracy, we're going to deploy that model to the cloud so that we can have a third party make predictions against that model over the internet. So we'll start here by loading our raw data, and I'm using just a publicly available data set about Boston area suburbs circa 1978, and it's hosted in a Google Cloud Storage bucket. So this code here is just downloading that CSV file from the Google Cloud Storage into a couple of Python variables in memory. And here I'm just going to print out the first few rows of that data so you can see what it actually looks like. And this may be the first live coding stall here, so bear with me. Just going to refresh this here. So this is running off of a virtual machine in the cloud, and that virtual machine lost its connection, probably because I was doing the slides for too long without refreshing this, so I'm just reconnecting here. And while this is coming up, what I can do is skip to the second step here is, once you have your raw data loaded, so in this case a CSV file, the next step that you want to do as a data scientist is explore that data. Understand, first of all, is my data clean? Do I have outliers? Just do a sanity check that the data makes sense. And then second of all, do any transformations that I need to do. So this is a tool called Google Cloud Data Prep, and it's nice because right off the bat, when you upload a CSV file, it already builds these histograms of all your fields for you. So, for example, I can see that the field here, the age of the house, the range is between 3 and 100 years old. That's how old these houses are. And it's more concentrated towards the upper end. So I have more houses that are old, closer to the 100 years old, than that are brand new houses. And then if I click Edit and then Column Details, I can get my basic statistics about that particular column, my min, median, standard deviation, my quartiles, and things like that. And let's say that I want to do some manipulation on this data, then I can just choose a transformation here, and there's different things I can do. I can do aggregations, I can flatten, I can join, I can pivot, I can do windowing. So a lot of your basic data manipulation here you can do through this graphical tool. And the nice thing about this is the output of this tool is a data flow pipeline. And data flow is an implementation of Apache Beam, which is designed to work on large out-of-memory data sets. So let's say that I've looked at my data, I'm happy with the transformations. Then at this point, what I would do is I would just export this data to a data flow job that would run the transformations, and then I could then pick back up with that data back in TensorFlow. And of course, this had to happen as I was doing the live demo. So it's provisioning the Google Cloud Shell machine, which is how I connect to the Data Lab instance. Google Cloud Shell is actually a free service, so sometimes if there's a lot of demand in a particular region, you have to wait a little bit to get a machine. So what I can do is, hopefully that will come up, or actually it may just be that my internet connection in general is not working right now. Yeah, I think that's what it is. Okay, there we go. So one of the things about working in the cloud is you actually need an internet connection for it to work. Okay, so let me spin this back up now. There we go. And I'm going to connect back into that instance. Okay, we'll give that a second. And while that's loading up, I'm going to continue on in the GitHub repository here. So now that I've loaded my raw data, I've explored it, I'm happy with what it looks like. Now I can actually start writing my TensorFlow code. So to write my TensorFlow code, there's about 4 or 5 steps I need to do. So the first thing I need to do is define my data interface. I need to tell TensorFlow how to interpret the different columns within my data set. So there's different column types. You have continuous data, you have categorical data. So price, for example, is an example of a continuous variable. It can take any real value. Department in a university, for example, would be an example of a categorical value. So it could be one of a discrete set of things, math or English or psychology, et cetera. And each of these features are optimized in a different way by machine learning algorithms. So you have to inform the algorithm what type of data this is. And in my particular data set, it's pretty easy because all of my features are numerical real value numbers, so they're all going to be categorical features. So here, basically, I just have a for loop going through the features that I'm going to use for this, and telling it to treat them all as real valued columns. So that's my data interface. Now, the next thing that I need to do is pick out my actual estimator. So my estimator is what you could think of as your canned model. And in this case, I'm going to use a neural network, a deep neural network. And the reason that I'm using that is because the relationship between my input features and the actual selling price of a house is nonlinear. So I'm not going to have a lot of success if I use something like logistic regression, whereas deep learning, the most common definition of deep learning is just a neural network with 2 or more hidden layers, is good for modeling that type of relationship. So my code for defining a neural network is just this cell here. And I'm specifying that I want 2 hidden layers, each with 10 neurons in each layer. So 10 neurons in the first layer and 10 neurons in the second layer. And that's all I have to do to define that. And I'm passing in my feature definition from the previous cell, so it knows how to interpret that data. So just take a second to appreciate that I could do that with just a few lines of code. Defining a neural network is typically something that's pretty involved to do. So that's the advantage of dealing at this higher level of abstraction. So then I'm going to define my input function. So at this point, I've just specified a data API, if you will, but I haven't actually passed the data in. So this data is actually reading from that pandas variable that I created earlier, which, if you remember, just pulled that CSV down from Google Cloud Storage and stored it in memory. And I'm saying that that's where my features exist. And my label, which is what I'm trying to predict, is going to be the feature that I've identified as label, which I did earlier on here, which is median value, which is actually sales price. So I've got my features and my labels, and I'm passing those as my input function. And then you have a separate input function for serving. So serving is just a synonym for prediction or for inference. So at the time when I have a user, a third-party user using my prediction service, they may pass in data in a slightly different way than how I trained on. So that's why I'm allowed to define a separate serving input function, which I do here. And I actually am not going to pass it in any differently. So the first part of the code is the same. And then there's just some boilerplate code here that you don't modify. And the last step is I'm going to package all of this into what's called an experiment. And an experiment is what allows me to actually do this distributed training without having to write any additional code. And it's just a wrapper. So I'm just passing in pointers to all of these previous cells that I've defined in. So my input function, my estimator, and then I am specifying that I want to train this for 3,000 steps. And then at the end, I want to do an evaluation step to see how good this model is performing against my evaluation data. So that's all the TensorFlow code. And so my code is now written. And in order to train this on the cloud, I need to package this as a typical Python file. So here I'm just taking all of these individual cells and pasting them into a single cell. The code hasn't changed. And then at the end here, there's some boilerplate code that you would just copy and paste that tells this program how to parse certain command line arguments that the Google Cloud ML engine expects. So at this point, I can actually train. And I'm going to train both locally and in the cloud, so you can see how both of those work. There's a couple cloud variables that I'm defining here. So this is the address of my Google Cloud Storage bucket that I want my model to be written to. This is the name of my Google Cloud project. And this is the geographical region that I want my virtual machines to be spun up on. And I'm just setting those as an environment variable so I can reference them in the remaining cells. And so first, I'm going to run this locally. And in this case, locally is actually still on the cloud because Data Lab is a cloud virtual machine. And you'll see that 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 finished pretty quickly. I have some more compilation warnings here, which you can ignore. This is just because I didn't compile TensorFlow from scratch on this machine, so there's certain optimizations it's letting me know that I can take advantage of if I want to. And if I want to run this on the cloud, then I use a command line tool called gcloud, and I just specify the path of my Python file that I had just written here to disk. So that's all my code cells, just copied, pasted together, and written to disk. I'm writing a pointer to that, so it knows where the code lives. And I'm referencing, again, my Google Cloud Storage bucket, so it knows where to output the results to. So I'm going to run that. And so this is queued successfully. And this is just running on one cloud machine learning unit, which is, you can think of as the equivalent of a local laptop. Now, here's the real power of me writing this using the estimators API, is I can just add an argument here that says --scale equals standard 1. And now that's going to run, instead of on one CPU, it's going to run across 10 CPUs. And similarly, if I want to run on a GPU instead of on a CPU, I'll change this scale tier to basic GPU. And in terms of pricing, a GPU costs 3 times as much as a CPU to run on. So as a user, your price performance would be, you just want to make sure the GPU speeds up your training at least 3x. That's your break-even point. And so there's certain algorithms where a GPU can actually speed up your training 40, 50x. And there's other types of applications where a GPU isn't that much faster than a CPU. So just be aware of that when you're deciding whether to train on a CPU or a GPU. And then lastly, I am going to run across multiple GPUs. So the way that you define this is a little bit different. I create a YAML file where I specify my machine type, and then I reference that YAML file as a command line argument. So it's still not that complicated, but it's just a little bit different. And so now I'm running across 8 cloud GPUs. And actually, in this case, those are NVIDIA Tesla K80s. So I'm running across 8 of those in parallel. So if I go back to the cloud here and click on ML Engine jobs, you'll see all of those 4 jobs that I just kicked off. And they're spinning. And you might be asking why this is still running if the one I ran locally finished pretty much instantly. And the reason for that is when you're running in the cloud, it's starting up the virtual machine from scratch. So the startup time for that is about 5 minutes, and then it runs the job. So you wouldn't actually want to run this particular job in the cloud because it's such a small data set. But when you're thinking of larger data sets where it's going to take hours or even days to run, then that 5 minutes becomes pretty insignificant in the context of the horizontal scaling that you get. And in terms of the logging for any job as it's running, you can just click View Logs here, and it'll give you a running output of the logs. So here it says waiting for job to be provisioned. It's still spinning up the VM. And then when the job is done, we can deploy that, well, we can inspect our results. So I'm going to go back into my Data Lab notebook here, and I'm going to inspect the results of the job that I ran locally, since that one's already done. And we're going to inspect the results using a tool called TensorBoard. And so remember, just to review at this point, we've started with the raw data set. We've done some exploration of that data. We then wrote our TensorFlow code to define how to interpret the specific columns of that data, and also what type of algorithm that we wanted to use for training. So in this case, we used a 2-layer neural network. And now we want to investigate the results of that training. Did it actually learn anything? Is it doing anything useful? So here, I'm going to click on my loss diagram here, and I'm going to expand this. And basically what you're looking for here is that this line goes down and to the right. That means it's learning something over time. And you can see, here's my training step here. So I have my 3,000 training steps. And then I'm running one evaluation step at the end of it. So just to do a sanity check here, my evaluation step at the end is saying a loss of 6.4 times 10 raised to 7, which might seem like a lot, but this is actually a squared error. That's how this is measured. So if I just do some quick math here, so I'm going to do the square root of 6.46 followed by, or let's just do 646 and then 1, 2, 3, 4, 5 zeros. So that's that same number. And so that comes to about 8,000. So if I put this back in my original problem, that means it's predicting the selling price of a house with an average error of about $8,000, which is pretty good. Maybe it could be better, but for any of you who ever sold a house or bought a house, if you could know ahead of time within $8,000 what it was going to sell for, you'd be pretty happy with that. So I've inspected my results. I am now happy with it, and I'm going to now deploy my model for actually for prediction. So to do that, there's another gcloud command here, and I'm just again pointing to the model file that was created. And what this is doing now is it's pushing my model, TensorFlow model file to the cloud, and it's spinning up some infrastructure to actually back that. And this is auto-scaling infrastructure. So let's say today that I only get, let's say I've just launched this API and I don't have any users yet, so I'm only getting maybe 10 requests per day. Then it's just going to have the minimal VM to back that. But all of a sudden, if that API goes viral and I'm getting thousands of requests per second, then this service will just spin up more VMs in the background to handle those requests. So it's a cloud-native, fully auto-scaling service in that sense. And I can see here, if I go to my models section and then click on housing prices, that it's creating that model. And this will take just about probably 15 more seconds, because it is spinning up that VM to back it. And then once that's done, I'm going to actually test it out. So I'm going to write out a couple of new records here for prediction. So I have all my predictive features here, the crime rate, the age of the house, the student to teacher ratio in that area. And I'm going to write those out to a file. And then I'm just going to pass that file to the service. And then here I get my actual predictions back. So $24,000 and $17,000 respectively. And keep in mind, this data set is from 1978. So those housing prices are actually, in US dollars, are past the sanity check. So just to review, what we covered here is how to use TensorFlow's high-level estimator API, how to deploy it for distributed training on the cloud, how to evaluate those results using the tool called TensorBoard, and then how to deploy that resulting model to the cloud for online prediction. And I also want to point out some important things that we didn't cover. So in this case, we were using a data set that fit in memory. And if you wanted to use a data set that was larger than memory, or a quote-unquote big data set, there's some other things you would have to take into account. We didn't do any true feature engineering. We just passed our CSV features as in without doing transformations, because in this case we didn't need to, but in most cases you will need to. And then lastly, we didn't do any automatic hyperparameter tuning, which in a real data science environment you would normally do that. If you would like to learn how to do those things, the last thing that I will plug here is there is a great course on Coursera that we released recently that covers how to do all those things. It's a 1-week course. It goes through a case study of predicting taxi cab prices in New York City. And it'll do kind of even a level deeper than we did today. So, yeah, apologies for losing the internet connection and not realizing I lost it for a couple minutes there. But thank you for bearing with me. I have technically 50 seconds for questions, but if we have any, I'm happy to take them.
And there's one here. Yeah. When collecting more data continuously, how do you use this data to automatically retrain your model? That's the question.
Yeah, so that's a good question. And that's a question that's very relevant for certain types of problems like recommendation engines, where you're getting new information about your environment and you want to retrain on a daily basis, maybe even an hourly basis. There's other types of problems where what you know about the world doesn't change for maybe 6 months or years at a time, so you don't have to worry about that. The answer is you just have to have a orchestration plan in place. So you need to have some type of messaging system that alerts you when there's new data to train on, and then that kicks off a new training job. And when that new training job is kicked off, your second decision point is how do I combine the results of that new training job with my old training job? So am I just replacing the old model completely with my new training data? Or maybe I want to do a sliding window where, let's take the example where I'm training on a daily basis. I want to take today's data and combine it with a sliding of the last 7 days data that I trained on. Or maybe what I want to do is just an incumbent versus challenger scenario, where I take today's data that I trained on, evaluate the model against my success metric, and see if it does better or worse than my incumbent model. And if it does better, I promote that to production, or if it doesn't do better, I stay with the incumbent model. So there's a couple different ways that you can do that. We're working on some managed services coming out to make that orchestration piece even easier. Right now, you have to do it a bit more piecemeal, but it's very similar to problem to kind of continuous integration, continuous deployment tools in the non-machine learning sector.
Okay, we're out of time, and thank you very much, Vijay.
Thank you.